This video is for The Living Earth, Unit 3.3, Evidence for Plate Tectonics. Today's essential question is, what is the process of seafloor spreading? Our first main idea, seafloor spreading. Earth's crust and the upper part of the mantle make up the relatively cool, rigid outer layer of the planet. This cool, rigid layer is called the lithosphere. The lithosphere is separated into tectonic plates. The tectonic plates are constantly moving together and apart. This phenomenon is known as the theory of plate tectonics. The theory of plate tectonics explains how Earth's surface is recycled over time. Plate movements are responsible both for the formation of certain features on Earth's ocean floor and continental crust, and to a lesser extent, for the distribution of Earth's rocks and minerals. Tectonic plates are destroyed at subduction zones. Subduction zones are areas where a denser plate slides beneath a less dense plate. The denser plate then melts in Earth's mantle. New oceanic crust is formed at mid-ocean ridges. This happens through the process of seafloor spreading. Mid-ocean ridges are oceanic rift zones. They consist of long mountain chains along a central rift valley. Mid-ocean ridges are divergent plate boundaries. At mid-ocean ridges, tectonic plates move apart and seafloor spreading occurs. Seafloor spreading is the process by which new oceanic lithosphere forms at a mid-ocean ridge. As tectonic plates move away from each other, the magma rises from Earth's interior. It then cools and solidifies in the center of that ridge. The rising magma at the mid-ocean ridge pushes up between the plates and drives them further apart. A new crust is forming at the spreading center, and as it does, it pushes the older crust apart. Because of this, the oceanic crust contains symmetrical patterns of crustal rock ages. These rocks increase in age as their distance from the mid-ocean ridge increases as well. Our next main idea, learning from mid-ocean ridges. The patterns that form at mid-ocean ridges reveal additional information about Earth's history at the time that the older crust was formed. For example, Earth's magnetic field occasionally reverses its polarity. Earth's magnetic field is generated by the flow and circulation of the liquid outer core around the solid inner core. This magnetic field is not static, which means it moves all the time. For this reason, magnetic north and true north, meaning the north end of Earth's rotational axis, do not always correspond. True north is a fixed geographic location, but magnetic north is what attracts the needle in a compass. Magnetic north migrates over time in a phenomenon called polar wandering. So, magnetic north does not always match up with the true geographic north. The angle of this difference at any given location is called the declination. The declination can be set on a compass to correct for this difference, and maps often include it as well. Polar wandering is a continuous process that occurs on a human timescale, meaning not geologic, a reasonably short timescale. Magnetic north has shifted several degrees within a period of a few decades. In addition to the poles wandering over the northern and southern hemispheres, Earth's magnetic poles completely flip. Throughout geologic history, Earth's magnetic field has completely reversed many times. When Earth's magnetic field reverses polarity, the same end of the compass needle still points to the magnetic North Pole. However, the magnetic North Pole would be located closer to the geographic the geographic South Pole. After another pole reversal, the poles switch back so that the magnetic north is again closer to the geographic north. These reversals have happened many times throughout Earth's history, but they do not happen at a predictable rate. Over the last 20 million years, there has been a magnetic pole reversal on average about every 200,000 to 300,000 years. However, much longer periods have passed without any pole reversals. Scientists can study these magnetic pole reversals by studying the magnetic polarity of rocks in Earth's crust. Spreading centers, like the one you see on your screen here, are an ideal place to study this phenomenon because rocks on either side of a mid-ocean ridge can be matched and correlated. The oceanic crust contains symmetrical bands of alternating magnetic polarity on each side of the mid-ocean ridge. Scientists are not sure exactly what the effects of a magnetic field reversal would be on living things. However, it is unlikely that a reversal would be harmful to most life on Earth. Although Earth's magnetic field protects the planet from solar radiation, the atmosphere also protects the planet from the sun's harmful rays. Animals that rely on magnetic fields for navigation and migration would likely be able to adapt since pole reversals seem to occur very slowly in relation to an individual's lifespan. At this point, you should be able to generate a full and appropriate response to today's essential question. What is the process of seafloor spreading?